Corinne, you can get started.
Are we ready to go? Okay, awesome. Well, welcome everybody. So I guess the third or fourth in this this series research workshop. So this is today on offshore wind energy. I'm going to give a little kind of background or some thoughts, try and keep myself on time, and then we've got a number of speakers today on the topic as well. So really looking forward to this. I'm going to see if I can share my screen successfully here. Is that the right screen?
Yes.
Okay, perfect. Okay. Yeah, so the topic today is offshore wind, and we've got a talk on social integration as well. So should be great. This is a shot of Canada generation sources right now, just to give us a little context. The lighter green there being wind. You can see pretty much all onshore at this point. Out here, I'm sitting here in Victoria, out of British Columbia. So we have a couple of remote wind farms, and then kind of across the country, various different folks building different things. This is kind of why one of the main reasons we're here. If you look particularly on the east, west, and north coast of Canada, this nice kind of purplish color is extremely high wind speed. So there is a lot of offshore wind potential resource out there. Unfortunately, it's not necessarily next to major grids, and that's one of the challenges with offshore wind energy. This again, just a little BC context. So we're building this large thing called Site C, large hydro dam. Originally was going to cost 8 billion, got to 12. We're up to 16 and counting. And when you start kind of, I don't think we're going to be building large hydro again in this province. Muskrat Falls, things like that on the East Coast, also similarly challenged. So this is one of the reasons for looking offshore is kind of the next frontier. This was BC Hydro, so our provincial utility, recently did their resource options report. This is from their draft a little bit, but it's basically the same. And just to point out here, so this is wind, their BC Hydro's own numbers, wind offshore, what they call point of interconnection. So this is actually getting it back and cooking onto the grid. They're getting numbers, and they kind of look at this incremental rollout. And you can see here that there is wind energy that's probably offshore wind energy that would have even been cheaper than the costs roughly that we might be ending up with out of Site C. And this is what Site C is supposed to produce at 5,100 gigawatt hours. And we're potentially a large amount of that could have been offshore wind. So looking to the future, this is kind of what we're thinking about. Here, we've been looking at offshore wind for some time. We did some work looking at different floater designs. We like to do optimization of things. So some simplified linearized hydrodynamics model, mooring line models, and really trying to look at this whole spectrum from spar buoys to buoyancy stabilized platforms, TLPs, things like that, and get this Pareto front trade-off between cost and performance. In this case, it was tower head acceleration. And if you look internationally, there's, I would say, somewhat of a convergence towards these more buoyancy stabilized type platforms, but it's still a lot of different options out there. So it makes for an interesting design question. And also a lot of local manufacturing content when you go to build a lot of these offshore installations. We also have here over on the West Coast, this FLIDAR buoy that we've got at Prime, the Pacific Regional Institute for Marine Energy Discovery. I run with another prof here, Brad Buckham. And this was a CFI purchase we got recently and deployed. So up here is a LiDAR head looking upwards to measure winds aloft up to about 200 meters. Got some solar panels and wind turbines to keep it ticking along. We've deployed it here just off of Victoria for like a shakedown cruise. And then we're also going to have a shore-mounted LiDAR to compare this moving floating LiDAR to that. So getting into some resource assessment work. Another major project we've got going on here is solid carbon. So this is looking at using offshore wind for direct air capture or carbon capture, and then eventually sequestration of that carbon. So this is a core from Carbfix over in Iceland, where they've injected CO2 and it's turned into this carbonate rock. We're looking out here on Cascadia. This red dot out at sea is where we could inject it and hopefully have something similar happen. And then this blue area is the offshore wind potential. We've been mapping out kind of potentially where you could build these systems. And we're taking a look at driving these thermochemical processes using offshore wind in an off-grid type environment. So using this resource that could be challenging to grid connect, but to do CCS activities. You can also, turns out, do seawater capture. So we've been taking a look at that, as well as this is Climeworks out in Iceland, their recent install of a direct air capture facility. So we'd be looking at taking those kind of units and putting them on a floating platform. And it turns out the powers and sizes actually kind of match relatively well. So that's been encouraging work. This is our overall system framework. We're looking at optimizing different configurations from near bottom mounted to more floating configurations, looking at transporting CO2 around, doing injection far offshore. We're also looking at some wind-driven ships and mobile wind platforms and other more blue skies research ideas, again, to try and capture that offshore wind potential, but not necessarily even having to worry about mooring and some of the other legal regulatory things that go in there. Off of that, we've also looked at using offshore marine or offshore wind energy combined with direct air capture, and then we add in some electrolysis to make synthetic fuels. So we've looked at methanol, methane, etc., and some of those potentials there, again, combining wind power with these different thermochemical processes, and also looking in particular at just neat hydrogen production as well as ammonia, which has there's a lot of interest in that in the marine transport industry. So we're sitting on the ocean. It's potentially a good application. So all of these is basically to say, and if you look at the Europeans, there's a lot of activity in Europe going on around offshore wind plus hydrogen production. It's still nascent, but there's getting to the first couple of demonstration projects. And we think about Canada and geographic distribution, location of grid, etc. There's I think good potential here as well for the non-electricity type uses of offshore wind. Obviously, lots of challenges, big waves, this kind of thing. So with our solid carbon project, looking at some of the marinization and corrosion aspects of this, how do these DAC sorbents work offshore, etc., and different system level implications, in particular some of the O&M requirements, things like that. So it's not necessarily easy, but there is a lot of resource there, so worth taking a look at. Some of the work we've been doing as well with solid carbon, because it sits in quite deep water as well. On the west coast here, our shelf falls off relatively quickly, so relatively deep water. Trying to push some of the models that are out there. There's Wisdom Plant, and Gerard's been looking at trying to examine cost models as you go towards deeper waters. What does that mean in terms of cost progressions into deeper depths? There's some interesting paper, if you haven't seen it, for last year Nature Energy paper looking at predicted cost progressions. And this was done by expert elicitation. So you go to people in the industry and ask them, where do you think are costs going over time? So they've got some different spreads, right? But you ask different people, you get different answers. They're looking at onshore, fixed bottom offshore, and floating offshore. You can ask people in different jurisdictions. So there's where you get the different colored lines, and then percentile ranges. You can see LCOEs on onshore. There's not as much room probably for price progression, but certainly fixed bottom and floating offshore, lots of room for growth. And then when you look out to that kind of 2050 period that everyone's talking about now with net zero futures, you start getting into the realms of possibility on costs and relative costs of different technologies. This was done just published in the last year. What's really interesting, they also looked at what back to their study they did in 2014, and you can see again these shaded areas were what the experts at that time thought would happen, and then the solid lines are best estimates from actual data over those previous years of what actually happened. You can see, interestingly, cost progressions actually dropped faster than people thought they would. So we're learning and figuring out how to do this even more rapidly than we expected. And with that, so I think there's a huge amount of opportunity in Canada for this, and glad to have this research network bringing us together to talk, particularly coast to coast. There are kind of different, I don't know, circumstances, regulatory structures, utilities on the different coasts, but I think there's a lot that could be done in Canada, this area, and we really need to have some coordination between researchers across the country and industry to try and really get this going in Canada. So I'll hand it over to Lindsay to talk about that wider perspective and context.
Thanks, Corinne, and I'll just let Marianne put up our welcome slides. Okay, so welcome to everyone joining us today. We're excited to have everybody back. And if this is the first time you've come, I'm just going to go over a little bit about what the Canadian Wind Energy Research Network is about. So we have some goals. First, to create a forum for collaboration, and this has worked really well throughout the last year. We've seen lots of collaboration come from the network that we established about a year ago, a little bit over a year ago. The other goal is accelerate and uptake the impact of research products. So the network includes membership from the universities, from independent research organizations, from industry and government. So we're really looking to establish collaboration and research projects amongst all different types of stakeholders in our membership. The network is interested, in all stages of wind energy research, from fundamental to applied, and believes that collaboration will result in the high level of innovation that is required to advance the wind energy industry. Next slide. So our goal is to hold at least one meeting a year. So we did have a meeting last year, and this is our second meeting. Members with intersecting areas of interest are encouraged to engage in joint research and to pursue external funding opportunities. And we've seen some of this happen. So people are connecting outside of the times that we're meeting and getting together and joining some projects and looking for external opportunities to pursue those research opportunities as well. So our steering committee would like to welcome you today. And our members of our steering committee are Ryan Kilpatrick from CanMet Energy, Natural Resources Canada, Dr. Rube Carbo and myself from the University of Windsor, Phil McKay from the Canadian Renewable Energy Association, Charles Gaudreau from Nergica, and then Scott Harper and Marianne Rogers, both from WeCan. So like I mentioned, this is our second meeting. So for this meeting, what we have is a series of webinars with short presentations, followed by a brief discussion. Today is day 4. So if you've joined us on day 1 through 3, you've had an idea of what these webinars look like. We are hoping that we'll be able to meet in person for future meetings. That is the goal. So hopefully going forward, we can have some in-person meetings. So day 1, we covered wind turbine aerodynamics. Day 2, we covered wind integration and curriculum development. Day 3, we covered cold climate and forecasting. Today is day 4. We're talking about offshore wind, and we just heard from Corinne on what we can expect on some of those topics. We'll also be covering social and environmental integration. And then our last webinar in the series will be on Wednesday, and we'll cover asset management. And we'll record these and share them with the research network following that last meeting there. So with that, I'll give it back to Corinne to take over and get on to our speakers. So thanks everyone for joining us today.
Great, thanks, Lindsay. So we've got a couple different speakers lined up. I'll try and give kind of a 1-minute warning, where I guess it's kind of a punchy format of kind of 5 minutes apiece. So we're going to lead off with Leandro talking about some LES simulations of offshore turbines.
Perfect. Thank you. Hi, everyone. Everyone is listening? Perfect. Let's go then. I'm going to share my screen here. You guys seeing that?
Yeah, looks good.
Let's give it a presentation. So we're going to talk a little bit about our project, large edge simulation of atmospheric flow around wind turbines with the use of immersed boundary method of the NRL 5 megawatt. I'm Leandro, an international student, PhD student at UBCO CFD lab, supervised by Professor Joshua Brinkerhoff. So basically, we did a CFD setup and some simulations through LES of the NRL Offshore 5 megawatt. Lagrangian mesh represents the wind turbine of the SL, very well refined. And I also took up with the IB method. We have a Eulerian mesh that represents the flow over the WTG. And we have more than 1,000 probes installed to capture the data statistics and every data that we wanted. we inserted some initial and boundary conditions, which means U velocity at 8 meters per second. At the inlet, we are taking a CFL of 0.5.
Are
Yep.
you want to be on your second slide?
Yes,
Okay,
exactly.
we didn't see it switch over here.
Oh, my bad. Let's try again. Going for the second slide.
It still didn't. I don't know if anyone else is seeing it, but I'm still on the first slide.
Yeah, we don't see the presentation view, Leandro.
Oh, I see it. I will stop again and try to share again. Stop sharing. Sorry about that. Let's try over. Are you guys seeing right now?
Looks good. Yeah. Awesome.
All right, perfect. Sorry about the first one. And then we do have a last simulation of the NRL 5 megawatt. This is on the right side. It is a figure of our Lagrangian mesh, which represents the IB method with the STL. And we do have a Eulerian mesh that represents the flow over with more than 1,000 probes installed and placed like this figure. Initial boundary condition where the wind speed goes for 8 meters per second at the hub high for the inlet conditions, and we do simulate up 1,200 seconds for the physical time, and it's not appearing here, but we do have a variable time step which goes for 10 minus 4 to a 10 minus 5. Yeah, it's not going. You'll have to stop again. Sorry about that. I don't know what's going on with the presentation.
Yeah, sometimes presentation view just doesn't want to play. So you just look at a normal view, make it as big as possible.
Yeah, I will try in this idea.
There you go.
Are you guys seeing the presentation again? Sorry about that.
Yep.
All right. So the code that we simulated, it is an in-house code developed at the MF Lab at the Youth University, Federal University of Uberlândia in Brazil. So I'm from Brazil, and then we did have this exchange part of 6 months between Brazil and Canada at UBCO. So the code is basically based on Fortran, C, and C++. And the whole idea of the code that uses adaptive mesh refinement. Let's see if I got a play here. And the code is basically developed for turbulent and multi-phase flows. And the results that we're obtaining right now, it's preliminary results, which are doing very well. And then the next step that we're doing right now is install TI information in the inflow conditions so we can better represent the inflow conditions. But overall, the results that we are obtaining in terms of calculating the energy and the energy generation are pretty close, where we have like this green, this blue line represents the NRL experiment, and then we get our signal in gray, which represents our simulation. So we're doing better, really good, actually, less than 5% difference from the experiment. Yeah, it's a quick presentation actually, and then this is basically in 5 minutes what I can get you guys. But yeah, our code are doing really well, and we are also comparing with different codes, getting really good results. And Professor Joshua are working with other PhD students, doing really well with the Tosca code from UBCO, which represents a really good wind farm layout and the interactions between wind farms as well. So thanks, Kerwin. Sorry about the presentation problems here.
No worries. I've had that lots of times. Great, thank you. Thank you, Andrew.
Yeah, if you guys have any questions, just a quick look what I'm doing right now. But yeah, it is, we are getting really great results from that.
Awesome. I think the idea is to have kind of hold questions to the discussion at the end.
Perfect.
So we'll keep rolling. Thank you. Next up, we've got Jordan. You online there. I don't see him in the.
Jordan isn't able to attend today,
Okay.
so we'll just skip him.
Keep going. All right, Christopher. I'm gonna mangle your last name. Niazriki?
Yeah, I'm just, I thought I had 5 more minutes, but that's fine.
Throw you on the spot.
Okay. Let me share my screen as well.
So you're coming out to us from Massachusetts then?
I am.
Excellent.
Right. Can you see my screen?
Looks good.
Okay, wonderful. So my name is Chris Niazriki. I'm the director of the WinStar Center, which is an industry university cooperative research center in the United States. It's supported by the National Science Foundation, and the lead institution is the University of Massachusetts Lowell. Our partner is the University of Texas at Dallas. And so I'm just going to give you a quick overview of what we're doing. There's a few other things related to offshore wind within the United States. There's a National Offshore Wind Research and Development Consortium that's out of Stony Brook University. So they provide funding from the Department of Energy to support research with and collaboration. So that's one activity that's going on. There's also within Massachusetts, there's a partnership for offshore wind energy research. It's a collection of different universities that include UMass Amherst, UMass Dartmouth, Tufts, Northeastern, Woods Hole, Oceanographic Institute, some other universities as well. So let me tell you a little bit about WinStar. It is the way it works is that the foundation for it is a collection of research projects, and those are supported by industry members. They're supported by the National Science Foundation, and they're also, the universities provide cost share. Those research projects are selected and driven by the companies that are participating in the center. And we basically work on those projects. We do whatever they tell us to do. They select the projects that we execute, and they're extremely relevant to the industry because they're deciding what we do. So the goals within the center is basically to work on research that benefits the members, bring together university and industry to work on problems, leverage the capabilities and the expertise that we have at both universities, as well as train students and generate IP publications, those sorts of things. If you've been working in the wind industry, you know that companies can be quite guarded with their IP and that sort of thing. So we've created an ecosystem that enables sharing of ideas and collaboration. And so it's a nice forum from which to work. And I think it's unique within the United States. But ultimately, what are we trying to do? Trying to reduce the cost of energy by improving performance, reliability, better materials, et cetera. This shows the different companies and participants that are part of WinStar. So we have an OEM, which is GE. We have 6 owner operators, which are Leeward, Pattern, EDP Renewable, Shell, Avangrid, and Excel. TPI Composites is a large blade manufacturer. Olin is, and Westlake Epoxy are materials companies. And then we have other companies that are involved in structural health monitoring controls, which include Bachmann, Windesco, Arctura, TPI. I'm sorry, not TPI. So Arctura, Windesco, and Bachmann. And then we have a couple of organizations, Electric Power Research Institute, and also Mass Clean Energy, that are part of the center at the moment. We have a structure. So I'm the director. There's a site director at UT Dallas, and then we have an advisory board that is part of our center. Current advisory board chairman is Brian Hill from Bachmann, and our co-chair is Brandon Fitchett from EPRI. So in terms of the facilities that we have, we leverage the facilities both at UMass Lowell and also at UT Dallas. So there's lots of different facilities and labs that we leverage. So for example, the Structural Dynamics and Acoustic Systems Lab, that's a lab that I work in. So it works on structural health monitoring, vibrations, acoustics, those sorts of things. So I'm not going to go through all the different labs, but we have quite a diversity of them. UT Dallas has, for example, has a mobile research van with a LiDAR trailer. And so they go out and do measurements in the field on different wind farms in Texas and wherever else. They also have a boundary layer wind tunnel. So it's a large facility. And so that's looking at things like effects of aerodynamics on erosion and leading edge erosion and that sort of thing. It's also looking at turbine-turbine interaction between wind farms, looking at things like blockage of wind farms, et cetera. Close to our university in Massachusetts is the largest blade test facility in North America. It's the Wind Technology Testing Center. And so we do a lot of testing there on different sensing techniques and monitoring techniques for blades. And so that's a nice asset that we have. The thrust areas, the major thrust areas that we have within the center are composites and blade manufacturing, structural health monitoring, inspection, wind plant modeling and measurement controls, energy storage, grid integration, foundations, and towers. So you can see on the right is a snapshot of sort of where the projects that we're currently executing land. You know, at any given time, we're running probably somewhere between around 10 projects. And so our budget in terms of real dollars for executing those projects is about $800K a year, US dollars. So if you want to know more about it, we have a website. We also have an annual report and a webinar series and a mailing list that we send out to people. So, you know, we're open to collaboration. We're interested in, if it's possible to collaborate with Canadian institutions or companies as well, we're open to that. So that's basically my last slide and gives you an overview of what we're doing at WindStar. And my contact information is there, so feel free to reach out if you're interested. And that's all I have.
Great, thanks, Christopher. Great overview. Lots going on. Okay. So again, we'll hold questions to the end there. So Xing, do you want to? You're queued up there?
Sure, yeah. And we share my. Oh, sorry. To go to the first page.
Looks good.
So can you see it?
Yep.
Hi, good afternoon, everyone. My name is Jianxing Huang. I'm from Cameron Energy Ottawa, Natural Resources Canada. Today, I'm going to do a presentation on the study, a preliminary study about the characterization of theoretical 900 megawatt offshore wind farm in Atlantic Canada. So here is an outline of my presentation. Okay, first the goal of the present study, some terminology, and the power density is a very important factor in the offshore wind study. So we're going to spend some time on the power density statistics, okay, based on the data from existing offshore wind farms. So we are using we have used the wind pool to do the simulation. So I'm going to present some wind pool simulation result. Lastly, I'm going to we're going to have some discussion about the result. Okay, so the goal of this study is to get some general idea about the overall performance of a 900 megawatt offshore wind turbine with regular turbine configurations. Okay, I'm going to talk about what the regular turbine configurations later on. So we're going to discuss what's the impact of the row space, the spacing, that row spacing and column spacing, the impact on the following on a bunch of parameters and answering the following questions. Okay, how much ocean area do we need, and what's the annual production, what's the power density, and the park efficiency and that capacity factor. So here is some definition of the term we're going to use. Okay, power density. Basically, power density is the total installed capacity divided by total area covered by wind turbines. Okay, that's the power density. Water pocket efficiency. Basically, here we are talking about two power. Like one is the actual power generated by the turbine. Another power is that the power. If we don't take, if we assume that there were no wake loss, and then there were no interaction between turbines, that's another power. So pocket efficiency is basically the ratio between this the two power that I just mentioned. Okay, the wake loss is one minus basically the pocket efficiency. The net capacity factor is the ratio between the amount of energy of the wind turbine produced during a period of time and the amount of energy that the wind farm would have produced at full capacity. So here, when you implement the turbine in the wind farm, the turbine can be arranged into different configurations. Okay, where it can be arranged randomly, like you see here. It can be also arranged into regular configurations. You have here are some examples. Example of the regular configuration: parallel and arc with sim radius and arc with sim origin, etc. So basically, in this presentation, I'm going to focus on the regular rectangular configuration. Okay. So here, to my height, to move this because I don't see it. The power density statistics. Okay. As I mentioned before, the power density is an important driver for wind farm study. So when there's a need to determine what's the best, what's the suitable power density. Okay, because the power density is related. Obviously, the power density is closely related to the wake loss. A low power density generally improve the efficiency. As in this case, the turbine are arranged far apart. But when we arrange the turbine far apart, that means we need a larger area, and that would will lead to higher project costs and heavier negative environment impact. So there is a need to make some kind of compromise between the to determine the power density. Here, what you can see on this slide is the data from 29 European offshore wind turbines. Okay, you can see the years of first operation and the installed capacity, the total area in acres, total area in square kilometers, and the actual power density. So basically, that we can see that the two most recent wind farms in UK have very low power density. Let's move to the next slide. So the power density here is a plot against the commercial operation date. Okay, we can see the trend. The power density has a trend of decreasing over time. The average power density is something around 0.04 megawatt per acre, and the largest wind farm under construction in UK has a power density of 0.012, as you can see here. Again, the same data is plotted against the project area. We can see an active relation between the project area and the power density. You can see the two largest projects have power density of about is between 0.01, somewhere around 0.01 and 0.02. So here the power density is plotted against the project capacity. So as you can see here, our the 900 megawatts is located somewhere around here. So we consider the power density would be between the range of 0.01 and 0.02. So this is the range that we considered in our study. So now it's the information about our simulation. Now simulation was performed with the, as I mentioned before, with the software, commercialized software Wind Pro to evaluate the performance of the 900 megawatt wind turbine. So we have used 50 megawatt turbines for our simulations, and the turbines are arranged into 6 rows and 10 columns. Okay, and 196 simulations were performed. That means that means 14 row spacing, and the row spacing is changing from 2D to 15D. The D presented turbine rotor diameter. Okay, we've used as well 14 different column spacing. So here you can see the fourth red circle here. So that's the 4 sites we have used for our study. But for this presentation, I just focus on one of them, which is here, which is close to PEI. So the nearest distance between the site of study to the shoreline is about 30 kilometers. But the turbine position, the row of the turbines are supposed to be perpendicular to the dominant wind direction. So about the wind resources data, we use the data downloaded from the global atlas of siting parameters, okay, which is from this website, which had pretty good resolution, great resolution of 250 meters, and the data are available for 3 vertical levels, which is 50, 100, and 150 meters. The turbine we use for our simulation, it's a turbine designed by NRL, jointly by NRL and the Technical University of Denmark. So the turbine has a rotor diameter of 240, and the hub height is 150 meters. So you can see here, you can see the power curve and the power and the coefficient, the power coefficient. Okay, the designed coefficient of power coefficient is 0. Somewhere around 0.5, and the design and the rated capacity is 15 megawatt. Here you can see a curve of thrust coefficient.
Just to give a 1-minute warning.
That's a red line, yeah.
Sorry, 1-minute warning. We'll try and keeping on schedule.
Oh,
yeah.
Oh, I'm sorry. I've got to move. Okay, so the wake model, the model that we use is the Jensen wake model. That means the velocity is reducing from upstream to downstream. So the result I plotted this 7 parameters against the row and the column spacing. So basically we can, here you have the row spacing and the column spacing, which is the power density is changing for different row and the column spacing. Okay, for the spacing of 6 diameter and the power density is 0.04. Okay, for this and the next couple of slides, I plotted the power density in green and the efficiency in red. Okay. So the here from this slide, basically we can see when the row spacing and column spacing is reduced, the power density is reducing at something like 5 times of the diameter. The park efficiency is something around 80%. If we really want higher park efficiency, we need a spacing, a row spacing and column spacing of 12 to 13D. Here is allows you to get some idea about the area needed for the site. So if the power density is something like 0.01, we need an area of 370 kilometers. If it's at 0.02, we need something like 300. If it's 0.01, we need 370 square kilometers. If it's at 0.02, we need 180 square meters. Okay. So I'm going to move quickly. So here give you some general idea about how much energy that can produce annually. So the if the power for PDE equals 0.01, we can generate 3.9 terawatt hour per year. If it's at 0.02, it's 3.8 terawatt hour per year. So here give you some well, I can escape this one because I don't have much time. So here you can see the net capacity factor, okay, which is varying from 48.2 to 49.7. So here give you some idea, general idea about number of turbines per square kilometers. If PD equals 0.01, it's less than 0.2 turbines per square kilometers. If it's at 0.02, it's about 0.4 turbines per square kilometers. So that's the conclusion. It's this kind of simulation result have provided overall estimates. So for given target wind turbine capacity and turbine size, the simulation method can be used to recommend park area configurations, spacing, and etc. So this kind of information can be used as a reference for economic analysis. So we're going to perform more simulation for other sites with some weak model in future. Okay, thank you very much for your attention. Thanks the help from my colleague Ryan and Graham. Thank you.
Great, thank you. All right, and our last one, the offshore wind, our friends over in Dalhousie. Nathaniel, I think you're online there.
So let's stop sharing.
Sorry, I was muted. Let me organize my technology here.
Sounds good.
Share one window. That would be this one. Can people see my presentation?
Yep, looks good.
Excellent. All right. Okay, so I just like to start where Dr. Huang started before me, and that is with the great question of, if you do offshore wind, what is an appropriate size for an offshore wind facility? And Dr. Huang gave a table in his presentation of recent projects, and I just scanned it visually. I think none appeared in his table in the last 4 or 5 years that were less than about 200 or 300 megawatts. And that's a very interesting point in the context of the Maritimes, because we are a small place where 200 or 300 megawatts is a very large amount of energy. So a little bit of background. You had this same presentation, the same point, that once you get offshore, wind speeds are staggeringly good. This is just a little clip from the Canadian Wind Energy Atlas that I'm sure we've all perused from time to time.
We've got the same issue.
Historically, land-based wind
I think
development.
we're not seeing your slide changing. I think we've got that presenter view thing going on again.
Oh dear. I'm sorry, how was that resolved?
If you just escape out, hit escape. And yeah, perfect. And now we see what you're looking at. If you just try and make that as big as you
Okay.
can. There we go. Yeah, and zoom in a little bit. Yeah, awesome.
Okay. So historically, land-based wind has been targeting windy sites on land and doing a good job of it, and preferably sites that had an easy grid connection. The consequences of these motivations for the development of wind have been that a lot of wind has developed in the same places. Can you see my mouse?
Yep.
I'll just point to, this is the Cobquid Mountains, where you see this ridge that turns orange, where there are higher wind velocities. A huge fraction of Nova Scotia's wind is in the Cobquids here. PEI has an enormous proportion of wind development, and New Brunswick has a few farms scattered around looking and basically targeting these little orange dots. But the consequences of this development strategy is that a lot of capacity is in a few locations, and the resulting wind has fairly high autocorrelation. And by autocorrelation, I mean correlation between the sites, which leaves the grid having synchronized lulls in wind, where obviously some sort of replacement power is necessary. Turning to the topic of offshore wind, the resource everywhere is great, as you said. As Dr. Huang, or as I alluded to in reference to Dr. Huang's comments, the economies of scale are pushing for very large projects where 200 or 300 megawatts should be considered very large in the Maritimes. And at that scale, transmission limitations, consideration of those is critical in project siting. Of course, I threw in bathymetry. There's a mega grid push right now for the concept of the maritime energy loop, or rather the Atlantic loop. There's a huge amount of hydro that is generated in Labrador and in northern Quebec, and that flows down along one side of the Gulf of St. Lawrence. And as of recently, there's additional hydro that flows down on the east side of the Gulf of St. Lawrence. And the scales of these developments are, well, at least for the eastern bracket, the flow through the eastern path is 800 and 500 megawatts. 800 is generated at Muskrat Falls, this new mega hydro project that was developed in Labrador, and 500 megawatts is the nominal capacity of the DC link between Newfoundland and Nova Scotia. And that, I think, is really telling and interacts in an unfortunate way with discussion of the scale and potential of an offshore wind facility, where the minimum practical size may be 200 or 300 megawatts, and the most modern sites are often over 500. I'll just skip right along. These are the transmission limits as of the present day, or actually as of a few years ago, between the various provinces. Nova Scotia and New Brunswick is currently about 300 megawatts transmission capability. That just further emphasizes that point. I know time is pressing, so I'll just keep skipping ahead here. So the premise of this study is, if you have very large scales of infrastructure, transmission constraints are important. I also talk about the engineering. I make use of capacity factor being an engineering decision in how I build my model. I've basically skipped the discussion of how I've built my model, but we can get into that later if there's time. So looking at transmission considerations, here we start in some locations within Nova Scotia. So remember, there's a DC connection coming down from Newfoundland, and this is a site called Canso, and here we see there's 0, and basically transmission is always southwest bound through there, and probably has a technical maximum of around a gigawatt, and occasionally comes close to that maximum. So if you add to transmission southwest bound through Canso, it may be problematic. Similarly, there's a major substation in the center of the province called Onslow, and here we have several years, a histogram of several years of transmission southwest bound through there. And similarly, it's always going to the southwest. And it's presumably sized not much larger than the greatest observed load, greatest observed transmission through there. So again, if you increase that transmission, you may be problematic. Adding 2 more sites here. Here we have flows to New Brunswick. I'm sorry, this is New Brunswick. Flows from New Brunswick to PEI. You can see it's almost always positive to PEI. PEI has very small loads. We're down here in the 200 megawatts as the maximum load. Almost never net from PEI. And similarly, in Nova Scotia, the distribution of flow to Nova Scotia suggests that energy is almost always flowing from New Brunswick to Nova Scotia, which I just put these arrows in to sort of fine tune the description of where the grid capacity, the transmission capacity exists. Salisbury is basically a proxy for PEI in Nova Scotia, since they both go through one substation. And then looking at the Maritimes as a unit, the primary flows are in from Quebec. Here's Quebec to New Brunswick, which, as you can see, almost never drops below 0. And the flows from New Brunswick to ISO New England, which is down here. And similarly, the flows very rarely reverse and flow back into New Brunswick. So what does this say about where you could attach a 2 or 3 or 500 megawatt wind farm? Well, if you attach it anywhere here and attempt to displace generation somewhere else in this system, you are likely to run into congestion limits and frequently have to curtail and face other anti-economic or difficult to manage factors. And similarly, because the flow is almost always coming down through Quebec, you probably wouldn't want to attach up here on the Gaspé Peninsula. So this particular figure refers specifically to where you attach. It doesn't necessarily speak to where the farm itself is built. For that, we're going to move on. I'd just like to say there's a borderline here in Newfoundland, and where that borderline should fall would be a function of internal transmission constraints and internal loads, and also the size of the proposed project. Newfoundland's population is about half of that of Nova Scotia. So again, the scales of transmission and the scales of power flows are similarly modest.
Just to give you a 1-minute warning there.
Okay, thanks very much. I think I can power on. So basically, the structure of my model is I took data points using Met towers and offshore buoys, as well as some model data. The orange is model data. And I looked at the manner in which the wind resource varies. And then I mapped the variations in the wind resource and compared them to fixed parameters. So this is a map of the correlation of the wind at each given location to the existing wind in Nova Scotia, New Brunswick, and PEI. And as I alluded to, as I was starting to talk, down here in southeast New Brunswick and northern Nova Scotia and most of PEI, the autocorrelation, although it's not exactly the right term, is quite high at about 0.7. And it sort of makes a bullseye. And as you get further and further away from that centroid of wind, the correlation of the resource in a given location drops and drops, to the point that out in eastern Newfoundland, you're down at around 0.2, which I think we can say is basically uncorrelated. Another interesting parameter that I was interested in was time shift. So if you picture 2 time series of data, where the x-axis is time and the y-axis is the wind resource, and you take the correlation between them and then shift one by a certain amount of time and take the correlation again and then shift it again, you can find the point where resources have maximal correlation, and that is what I've called the time shift. So here we have a map of the time shift. And what the time shift means is if you have wind lulls, those wind lulls will characteristically happen along this axis at 0 hour, at along this line, they'll be there about 5 hours later, 10 hours later, and 15 hours later. So once again, if you syncopate your wind lulls or wind events by 15 hours, it's starting to get up into almost synoptic scale time spans. So that is very interesting from a wind sighting perspective. This is another correlation. This is the correlation to the net load of the 3 provinces, which is the load minus the wind generation. So you see here in the center of our bullseye, we actually have some negative values, which is to say, because wind is so dominant in the area already, that the wind resource is positively correlated with negative load because the wind impacts load so dramatically. And which is to say, additional wind that you built would still supply electricity, but it would supply it when electricity is not very much needed. One more consideration, here's bathymetry. As other people have mentioned, down to about 50 meters, which is to say the reds and oranges, you can build ground mount, which is likely more expensive. The first presenter talked about the expert elicitation cost curves. Ground mount is still less expensive than floating, although floating, which obviously is suitable for practically arbitrary depths, is also falling. And so, thank you. Let's just put these together. So here are areas where you wouldn't want to attach. Here are areas where the correlation to the net load is poor. And here are areas that don't have much time shift, which is to say the lulls happen at the same time that existing lulls happen. And that, I think, is where I can stop. But I will just point out there's an area here off Grand Manan Island. There's an area here off Tusket, Nova Scotia. And also of interest, I think, would be Eastern Newfoundland. And those areas have several positive characteristics with respect to the wind resource.
Okay, great. Thank you.
Thanks so much.
Good. I love statistics. That's good. Nice.
I made fun maps.
Yeah, awesome. Okay, thank you very much. And then our final speaker today, Jamie Baxter, looks like you're online there. Switching over to the social environmental integration piece. So quite interested to see your findings here.
Thanks, Karen. Let me just get this all set up.
So this is an area that doesn't get enough addressing until too late. There's certainly been the experience out here in British Columbia. I think going on a decade ago, there was a large gigawatt scale farm proposed up in Haida Gwaii that didn't do the public relations engagement piece very well, I would argue. So hopefully we're learning as we go here, and looking forward to this, Jamie.
Okay, can you hear and see? All good? Okay, yeah, indeed. So I was thinking about the previous talk, Nathaniel's talk, and about tying in from offshore, and certainly offshore is on the radar of all those of us who do sort of community acceptance work. And as if you didn't have enough problems, technical problems, the people just make it that much more problematic. And I'll give you an example of why that's so important later in the findings. So what I'm going to talk about today is a project we've been doing for about 5 years now. It's called the Meaning of Community Wind Energy. And it takes what we have learned about the community, sort of community acceptance of wind energy at the local level, and taken some of those ideas to develop them and test them, particularly the idea that community-based wind energy is the better way or best way to go. So the context of this, if you didn't know already, if you're in Ontario, you know this very well, but you've probably seen it in the media elsewhere as well, that there's growing resistance, and certainly in our group in Task 28, so that's the social science of wind energy group in the IEA, things are getting worse. There's a consensus that things are getting worse socially, When I started doing this work about 10 years ago, we were looking at sort of positivity rates, acceptance rates as high as 80%, even in the local community or in the local community around the wind turbines within 2 kilometers. And now they're getting down to the sort of the 60 range. So we need to be doing things differently. And of course, in Ontario, we have a moratorium right now because of all the hubbub, partially because of the hubbub that was created around wind turbines. So acceptance is declining overall. And this is an example of some signs from a community meeting we went to about a decade ago. The meaning of community wind energy project is multidisciplinary. It involves Ontario, Nova Scotia, Ireland, as well as one First Nations community, the Chiging First Nation. They have their own 2 turbines. And we're basically testing, this idea of community wind from all these sort of national, provincial, and different types of community angles. It involves 5 faculty, a number of students, and there's only one student in this group that I show you. There's only one yet to complete, and she's doing the work with Chiging. There's 4 sub-studies involving qualitative methods, survey methods, and discourse analysis. What I'm going to show you is some survey results as a window into this literature, which connects with the European literature and some American literature. Called there's a study called the Wind Neighbors study. So some of the items we use in our survey are linked to that one. So in terms of how we think of social acceptance of wind energy, and in case I have to say it, this is onshore wind. We don't have any offshore wind in Canada. So onshore wind, we start with the basic framework of NIMBY. Everyone's familiar with that idea, and that's what I think a lot of people at the coffees at various conferences will say. Well, it's really just NIMBY. The literature and researchers in my area have done a lot to sort of debunk that idea. It's not that NIMBY doesn't exist, it's that it's a really sort of simplistic explanation. Plus it's pejorative and it just gets people's backs up. It paints these communities as more selfish than they probably are, and doesn't shed enough light on the process and the development itself. So we've moved from this framework on this side, which is well known in the literature from Walker and Divine Right, which says that there's 2 main dimensions. One is the process, which should be participatory, as opposed to closed and institutional, and the outcomes. If you want to simplify it, the benefits should be local and collective. So that's where the quadrant in green is community-based. The one that we sort of have done in Ontario, most places have done, is developer-led, where it's sort of there is opportunities for offshore companies to be involved, and the process is fairly closed. I used to work in the social construction of risk around waste sites, and there was a lot of talk about went from sort of the type of siting that's done in the wind energy industry to voluntary siting, which is a very different way of doing things. So this process outcome space, we looked at that in our group and said, well, is there anything else that's missing if we do a sort of scan of the literature? And we basically transformed this idea into a process benefits. So we took outcome and just called it benefits. And then also looked at investment scale, because these community-based wind projects in Denmark, for example, they're co-ops. Basically, locals can invest and they can profit from it, but it's sort of a co-op investment model. So we added this 3rd dimension and took the origin as the ideal in terms of community-based wind. So if it's local scale investment and returns, participatory, and the benefits are collective, then that's strong community-based wind. So from this literature, we formed three hypotheses. The first two are really the hypotheses. The third is basically just a robustness test. Positivity towards wind will be higher if the project is community-based. And those three dimensions that I just showed you will be predictive of positivity towards wind. And then the third one is these relationships will be robust in a model that includes all kinds of other significant predictors from previous studies in the literature. And this literature is going on 40 years now. So it's quite well developed, and you'd think we'd have more frameworks, but nevertheless, here we are.
Just to give you a time warning, Jamie, just to keep rolling.
Yeah. So sorry, how much time, Karen?
Officially 1 minute, but.
Oh, so I was told that it was in the timing that I saw it was 15 minutes.
Oh, do you have 15? Okay, I may have that wrong. Sorry.
But I'm going to try to be less than that. Is that right? That was my understanding with Mary Ann.
If that's what you were told, then go for it. Sorry.
Okay. The research design for this. So I'm just going to talk about Nova Scotia and Ontario. The Irish results are in. We just haven't processed them yet. Likewise for Chiging, we do have survey results for those other two areas, but they're similar. This is a mailback survey, so we mail it out and ask people to mail it back. We tried to get one each of a community-based and a developer-led project in Ontario and Nova Scotia. What we ended up was responses from 349 people. And you can see, so we use Guns Hill, Port Ryerson, and Ernstown, if you know these sites. And we were just talking about Nova Scotia, Eller's House in Terrence Bay, the other one's Chibukto, I think it's called, in Terrence Bay. So this is the way it shakes out in terms of delivering. What we did is a quota sample, a random quota sample. So we choose random mail routes within 5 kilometers, and then we mail out boxes of them in bulk. And so, and just to give you a sense of the size of the projects, they're fairly small. 10 turbines in Guns Hill and 10 in Eller's House. Those are the largest one. Those happen to be the community-based ones as well. And we have a response rate of about 22%, which is actually, it seems really low. And in terms of Census Canada, Stats Canada, this would be horrible. But in terms of social science research nowadays, it's actually quite good. I have two finding slides, and they're fairly straightforward messaging here. So there's two things going on here and a few take-home messages. One is that, so positivity here is in blue. And this is all the people, these are the decided voters. So taking the neutral out, and there's quite a few of those. But of those who are either positive or negative, overwhelmingly positive in Nova Scotia, just regardless of whether it's developer-led or community-based. And in Ontario, still majority, but much lower. So there's some sort of regional policy effect there. And ComFit is a big part of that, I think. In Nova Scotia, the community feed-in tariff, which led to the development of Eller's House. So the development type, so hypothesis one, the development type is not really significant, which is a little disappointing on some level, but there's some nuance to that. This is the regression model. This is a binary logistic regression model on predicting positive or negative. And the hypotheses are in the left column here. And hypothesis one, not a lot of evidence for that. Hypothesis two, this is the 3 dimensions: process, benefits, and the other one was investment scale. Investment scale didn't even make it to the model, and the reason for that is there was no differentiation in that variable. Almost everyone agreed, 90+% agreed that they want local scale investment. So that didn't differentiate anyone as a predictor model. So the finding isn't negative, it just doesn't show up in this model. So that's an important distinction. But the benefits predictor variables, they didn't show up in the model. We have one of the dimensions of process, fair planning, and that shows up as a predictor of positivity. And then we have a couple of variables from the long list of variables, sort of usual suspect variables in the literature, including trust in local government representatives, whereas trust in provincial governments didn't really matter, but trust in local governments really mattered. One of the reasons for that is Eller's House is actually a development of 3 municipalities in Nova Scotia, facilitated by ComFit, to invest in a project that is not necessarily in their backyard, unless you consider Nova Scotia your backyard. I know it's our ocean playground, but you know, the localness, the 5-kilometer localness isn't in effect at that level. But local governments figure heavy in that, because they are actually the owners of the turbines at Eller's House. Turbines are attractive in the landscape. This speaks to offshore as well, and this is the finding I said that is going to have implications. You know, you'd say onshore, well, a lot of these things don't matter because it's so far away from people. There's no health impacts, there's no vibrations, none of that. But the visual, we can't underestimate the visual impact. Extending the life of the turbines was also significant. None of the socio-demographic variables were significant in the models. So positivity is not, so community-based, you could conclude the community-based doesn't matter, but I think it does. I think the Eller's House example is, with a very high positivity, shows that it can work. But when it goes wrong, when you just use community-based in name and all the, you know, the fairness, they're focused on the process, then it fails almost horribly, not so horribly that you lose that majority support, but you have a lot more local conflict. So there seems to be a right way to do community-based. Benefits is a minimum for getting into the door. Yes, you have to have benefits at the community level, and they should be sort of collective benefits. They don't necessarily have to be individual benefits, although I have my doubts there. And the investment scale has to be local, but the procedure, so once those things are dealt with, then procedure. So, you know, when do you start the process? Do you have the developer actually knocking on your door and talking to you in person, and so on? So that these findings are really consistent with what we're also seeing in Chaging, which is a very sort of different situation, smaller number of turbines, but the community-based development has a lot of promise, but there's a lot of caveats that go along with it. Thank you.
Mute button. There we go. That's great. Thank you. Great insights there. Being similar when we looked at tidal and wave and others as well. It's interesting to see all these different pieces. So thanks to all our speakers. We've got some time now for questions and discussions. Marianne, what's our official, how long we're going for? It's about half an hour or so?
Yeah, I scheduled it to end at, in about half an hour. Okay. 20 minutes, yeah.
Great. Yeah, so the 5-minute format's always hard to get all the good stuff, and I've got lots of questions for all the speakers, but I'll open it up to people in the audience if you want to type stuff in, or kind of unmute yourself and ask a question, raise your hand, etc. I'm just looking in the chat. There were 1 or 2. Oh, Martin, you have a question there?
Sure. I can start. Jamie, really interesting talk. I was just curious if that community versus developer led can have a higher level dynamic going on, so that because we have so many developer led projects in Ontario, can you single out the community led one and say this is one versus the other? So for example, I don't know, I've been cycling around Port Virussy and there's so many wind turbines. Can you say people have an attitude about a community-led project versus a developer-led project when the entire region is full of turbines, where probably a lot of them are, and that's where I'm guessing developer-led. So maybe, like, is the overall thing dominating the opinion rather than a single project?
Yeah, so I'm a geographer by training, and one of the mantras in geography is the place matters, and this is the community wind and wind energy development is no different. The Port Virussy is very different in its structure, and that's where there was quite a bit of resistance because there was a group that was very organized against it. So, but you have these other communities where it doesn't even start, that kind of thing doesn't start. Does that have to do with the developer because they went and talked to people, knocked on doors, and spoke to the people living closest, not offering them a lease, but just talking to them? I think that does. And that's going to be the challenge for developers, is to think about how to do things without having a co-op, because I think our idea, we don't have a tradition of co-ops here the way they do in Denmark. So I think the Ellers House might work, but consider in Ontario where half the municipalities have basically said we are unwilling hosts. They've actually passed resolutions saying they're unwilling hosts to turbines. So it's a complicated landscape. Thanks for the question.
I think I see a hand up, but I can't.
Hi, it's me. It's Andrea. Hi, Jamie. Thanks for your presentation. I'm also a community energy power researcher, engineer, and practitioner. So I spent about 7-8 years developing community power using the cooperative model in Manitoba. Actually, we set precedent here. And so one of the things that we found was very interesting, and it took a long time, was that matching with the developer that was in the right mind and spirit to also appreciate and recognize the importance of the community structure. So I think that's a really important part when you're seeking out. It's not whether it's a developer using the cooperative model or the community or not. It's to be community led is really to have that community. I don't know, maybe it's even a grassroots similar to in Denmark, have that appreciation and work ethic of it being community led. And of course there are limits on that, but that's where, bringing in the specialists, the consultants to fill in the gaps of the community, because that's often a frustrating point as well. And, eventually it took us years, but I think, I don't remember how many iterations of developers we went through, but we were interviewing a lot of them to have the right mindset, to have that community mindset. So I think coming back to it, especially in wind, if developers, and there are benefits, there's a lot more benefits we see on the return on investment, like you mentioned, into communities when implementing the community model is so important. So having the developers adjust to the community, I think, is really important. It's a big shift. It's a business shift, a paradigm shift for sure. So yeah, so it's just nice to connect with you on community power and just provide a little feedback from my own experience.
Yeah, thanks, Andrea. I think that, coming up with a definition of what we mean by community-based is one of the steps, but I certainly think that there's ways that developers, can achieve the things that community-based development achieves without having the community investment. The communities, people don't have the dollars to invest in a local project. They don't have dollars to buy groceries. So why would they invest in a wind energy project? But there's other things that can be done that speak to the spirit of it, and the process is key to that. Yeah.
Yeah, and how we overcame that was by having the right business structure in place, because that was definitely one of the limitations with the scale and scope of wind projects, is the size that they are. You have to have the right business structure and to allow for different stakeholders and investment so that you can retain that community ownership model. Because I don't think that a developer, I don't know that they could achieve what a community could. Do you know what I mean? Because the definition, not just with the definition, but the ethos of what a community power project is different than, I think, the approach of a developer. So I don't know, it'd be interesting to see what would happen, but I haven't seen that in my experience.
Well, so that I referenced the Chiging community, what they did is flip the developer-led model. Developer came to them and said, would you like to do this? And they said, well, how would you like to be our consultant? And you do it for us, but we'll own it. The developer had actually proposed, we want to own it. Do you want to sort of have a share in it? And they said, no, we want to own the turbines. So
right.
That developer was open to the conversation. I'm not sure all developers like that, have that
right,
mindset when they knock on the door. Yeah.
Yeah. No, and you know what? I think, coming back to that portion, that there's some, that falls into the category of community for sure. I think so. As long as there's that say of the community. And I think that's the important part, is having that community involvement to the extent that the community defines as what works for them as well. Yeah, it's tricky. It's a tricky area, isn't it?
Definitely.
Thanks.
Yeah, a lot of our work here in the West Coast with First Nations communities and energy plans, and a lot of them currently for our focus is a lot on the off-diesel, off-grid ones. But again, in the history of BC Hydro, was a big IPP push with a lot of First Nations led wind, some of the wind projects, and then that program got canned, and there was a lot of animosity, but a lot of aspirations of those communities to do bigger things. So I was wondering too, with your work there, I think of Ontario, so there was a lot of we hate EVs, etc. And then just recently we're going to spend some billions on new battery manufacturing plants and things like that. Did you resolve anything to do with manufacture, like local manufacturing associated with wind? I think again, offshore wind, there's potentially local shipyards and things that would potentially come into it. So wondering what your insights might be there.
Yeah, there's people in Task 28 that are sort of going into that space now, and I think some people at Waterloo, Ian Rowlands is in that space right now. No, not sure exactly what they're doing. Chad Walker who was my former PhD student, is working at Waterloo on that type of thing. But no, I think that the next step, if I continued in the space, would probably be offshore, because I'm hoping, Canada is ready to take off now that Block Island's spinning, and the US is, that North America is now getting on board with the idea, and the excitement about it in our Task 28 of offshore. That's sort of where the excitement is right now.
Yeah. I don't know if Christopher, if you're still there, if you have any comment. I know in the US there's a number of coastal communities down there looking at big investments in port and operations facilities. Do you have any insight from the US side there?
I mean, the whole East Coast of the United States, multiple states, there's a herding mentality associated with offshore wind. So if one state starts leading it, the others start to engage as well. And that's really what's happening. So, Massachusetts was probably the leader in offshore wind initially. And then I think we're getting lapped by New York and maybe New Jersey, et cetera. So all these states there's active programs, and there's multiple procurements that are going on right now. And so at least on the industry side of things, that's where there's a lot of interest. In terms of, the biggest challenges are not necessarily the technical challenges, they're public policy, public acceptance. Those are the biggest hurdles I see in terms of advancing offshore wind within the United States. And so, the whole NIMBY thing is real, and getting approvals and policy, and people to not sue these companies to try to block things is huge. And so that's, quite frankly, in my opinion, policy and public acceptance are the biggest challenges.
I know when I arrived at MIT 20 years ago, the Cape Wind project was it was going to happen, and then it didn't. And that was 20 years ago. It's frustrating how slow things move. Yeah. I was wondering too, with Nathaniel, you were looking at the interties and transmission, and certainly building a transmission line, let alone a pipeline right now, also extremely fraught, or maybe even more fraught than the actual turbines themselves. And wondering what, in your modeling work, have you looked at that much in terms of constraints? Well, maybe he's not online still. Speaking to dead air. Okay. I don't know, Jamie, did you look at the transmission piece of it at all, or did that come up in your survey work?
No, again, this is a sort of a new area for others. That work's going on in the UK right now, but I haven't seen any results yet.
Okay. I think is there still a hand up?
That would be mine. This is Eldridge here from the Wind Energy Institute. I had a question and a comment for Nathaniel. I don't know if he's still around.
It looks like he's offline, and I don't see Lucas, who is the other rep. So I think we may be out of luck, unfortunately.
That's okay. What I'll do then is I won't ask the question. There was one comment I had, which is the fact that on one of his slides, he mentioned that it takes about 12 or 15 hours for winds to propagate across the Atlantic provinces. So say from New Brunswick out over the water, heading east. I just wanted to add a comment that's a line of thought that I'd never considered in the past, despite the fact that we operate a wind farm there. It had never really crossed my mind that if the wind speeds are going up on PEI, that means at some point in the past they were going up somewhere in New Brunswick, and then eventually they will go up further east. It's just a very interesting way to consider how wind propagates across the region.
Yeah, those are the large synoptic system, like the big weather system movement. Yeah, it was an interesting statistic.
Nathaniel is here, so Nathaniel,
Oh,
if
is
you
he?
wanted to comment on that.
Why can I not? Oh, I see him there, yeah. If he's maybe stepped away or. I was going to ask Dr. Wang, because you had specifically were studying a farm just off of PEI. Interesting work. Is yours considering the transmission intertie piece at all at this point in terms of those bottlenecks and power flows? Dr. Wang? No.
Anything? Are you there?
Dr. Huang, I think you're just muted.
Hi. Yeah.
Yeah, I was wondering in your work, did you have transmission intertie pieces you were looking at with the wind farm, and where exactly you were? Because I noticed you had a particular location for it. I was wondering how you arrived at that location to study.
Well, maybe Ryan, can you help me answer that question? Because that's based on something like an internal study to determine those kind of station, and the study result, like a report, hasn't been publicly published. That's why I didn't mention the detail. Maybe Ryan, can you make some comments on that?
Yeah, so the short answer is we're not really looking at transmission connection yet in our group, but certainly moving forward, we would like to combine our work with Dr. Pierce. We're mainly focusing on geophysical characteristics and human use and infrastructure, so things like fishing density, transportation, corridors, obviously wind speed, although the wind resource is excellent, but looking at the geology, and it's unfortunate that Jordan Emer wasn't able to present today because he had some new analysis on kind of foundation compatibility for different types of fixed bottom and floating foundation anchor structures. So we're looking at those and kind of combining them into a multi-criteria analysis, but it is missing that transmission interconnection piece. So I think that's something we can seek to combine our efforts on going forward.
You mentioned the social piece there. I was wondering, how does the east coast of Canada sit relative to, say, the North Sea and people that want to fish or move around in the waters? Do you have a sense of differences or commonalities we'd have with the European experience offshore?
That's not something I've really looked at too much. I don't know. I'm not sure if Dr. Baxter has a sense.
Yeah, in our group we have we have a representative from Japan, and this connection to the fishing resource. So your presentation, Kern, it struck me that, you know, with all those things, sort of things you can do offshore, the fishing part of it is the way this one project went in Japan, where they integrated with local fishers and came up with a scheme to help them increase their productivity in harvesting, and I think also do some farming, so fish farming off the so if we can come up with ways to connect with sort of what the locals are doing already, and then, I mean, in the Canadian context, First Nations would be absolutely critical, as you said earlier.
Yeah, see, Siemens had some bad news last week with their wind turbines. A whole rotor had fallen off, so they've now implemented exclusion zones around a couple of wind farms. So that's something to watch out for, I guess. It's just the news story.
Look up when you're harvesting.
Yeah, exactly. Eldridge, I see Nathaniel's back online. Did you want to ask your question?
Yeah, I will go ahead. Can you hear me?
Yeah.
Yes, I can. I apologize for taking another call. It was very rude.
That's okay. Nathaniel, do you want me to then repeat? There was a comment I had as well as a question. Did you happen to catch the comment?
No, I'm afraid I did not. If you could repeat it.
Yeah, I can repeat that. It was what I found interesting was the fact that you had a slide that showed the propagation delays, if you will, of winds across the Atlantic region. So my comment was more centered around the fact that despite the fact that so I'm with the Wind Energy Institute, despite the fact that we have a 10 megawatt wind farm on PEI, it hasn't ever crossed my mind the fact that if the wind speeds are ramping up on PEI now, and if the wind's coming from the west, that means the same thing has happened somewhere in New Brunswick at some point in the past, and at some point in the future, the same thing will happen further east. It's just an interesting way to present how the wind propagates across the region.
I would make a small correction. You're basically right, but even if the wind is coming from the east, the propagation of the weather system is most likely to be to the west, which is to say the east wind may pick up in Fredericton a couple of hours before it picks up in Wecan, even the east wind, because it is the nor'easter is being carried east by the jet stream.
Yes.
And that characteristic time delay is in effect mapping an average velocity of the jet stream carrying weather systems.
Okay.
In effect, I mean, it's not, it's observational rather than based on physics.
Yeah, that makes sense. I'll ask the question. You did have a slide there about loads, so demand on each of the 4 provincial grids. Have you thought about, or I guess what I should ask first is, when are those numbers from? The reason I'm asking is because I believe that some of those numbers have grown, and significantly, in the past year or so.
Yeah, that's a very good point. All of my numbers are a year and a half old or older. And interesting things have happened since then, of course. The connection of the Maritime Link and or I guess Maritime Link, I got some of that being connected, but Muskrat Falls coming online happened since then. And the load growth in Halifax, for instance, the population of Halifax has grown by 26% year over year. So yes, there are certainly refinements and modifications that will have to be made as new conditions apply. I didn't make any effort to try to project into the future to try to say what's going to be the case in the timescales of construction of a new farm. I only used historical data.
Perfect. Thank you.
I think I see another hand up. Ryan.
I just put mine. Yeah, so I have another question for Nathaniel. So as we contemplate kind of moving away from desktop analysis into collecting more data in Atlantic Canada, This could be in the form of new field measurement campaigns that measure geophysical, met ocean information, as well as potentially even related to species at risk and this sort of thing. One of the things we're trying to do first is kind of get a good sense of where the existing data has been collected historically. And so when you put up the slide about the network of meteorological buoys and towers, I was just wondering if you can comment, like I know some of these are operated by Environment Canada and DFO, but is there kind of a centralized source for all of this information, or did you collect a lot of that yourself? See you smiling a bit there.
Yes, great question. Actually, there used to be a centralized depot at American State University, the name of which I don't remember, but which I used. It basically just had any jurisdiction, any agency that monitors, that has monitoring stations and collects data, and you could download the whole thing, and you could format it how you liked, and pull the parameters that you were interested in and leave the ones you weren't. But that has since, last I looked, no longer does Canadian sites.
Oh, okay.
Possibly, you know, nationalism in research funding or something. So I think if your question is leading to the idea of, is that something that would be of value to researchers and should be reproduced, I would absolutely and fervently say yes. I think that would be a great resource.
Okay. Yeah, maybe we can connect offline. We have some meetings scheduled with some of our ECCC and DFO counterparts to try to put this all together, but could probably use a bit of your experience there as well.
Well, I wrote I'm not really a programmer per se, but I wrote a web scraper in MATLAB to go through the Environment Canada stations.
Well, yeah.
So don't do it that way.
Okay. Okay. Yeah, we'll connect later. Thanks.
Absolutely. Thanks.
That's great. Are there others online that we're holding a question or two? I was wondering, Nathaniel, on because you've got power flows, et cetera, did you look at market pricing for export, particularly to the US? I think New Brunswick and Nova Scotia, they're all vertically integrated utilities.
That's a really great question as well, and I'm glad you brought that up. Last week we saw a really interesting presentation by somebody from Alberta named Tyler or Taylor, a grad student of somebody's over there, who was looking at the basically the market price metric of the marginal utility of different wind farms. And no, we don't have that information. We don't have that data. They're all vertically integrated, Nova Scotia Power and New Brunswick Power. We don't have hourly pricing. I wish I did. I think that would possibly be a great shortcut to all of the important metrics. Okay, what's it actually worth? But so in a sense, everything I looked at was sort of a proxy for that.
Okay. But you have data. We have exactly the same problem in British Columbia. It's all behind a closed door. We can get hourly flows across tie lines to Alberta and the US. We've gotten maybe some kind of idea of generation, but it's a big black box, whereas you go next door to Alberta and you get nice 5-minute data as much as you want. So well, it sounds like the same.
It's worse than a black box. Those numbers actually don't exist, right? They're Schrodinger's cat. There is no market, so there is no actual discovered price. It's just somebody in a control room turns up a switch. There's no $ on the switch. It's just, that's the job.
Yeah. I know in British Columbia, it's changed over the years too. PowerX had a lot of money selling to California. And as I understand it, basically all the wind energy currently in British Columbia is sold to California because you get additional rocks and other things. That's why I was interested on the East Coast too. When you think about developing the wind, kind of how would the accounting actually work out on that in terms of like coal displacement locally versus selling into New England, et cetera. And that's going to change over time too, with all the development down in the US of the offshore wind assets. Yeah.
I suppose on my end, one could look up the historical New England ISO prices and tie that in and have at least one metric have at least one,
Yeah.
flow data point for price, but it's a lot of work for not a whole lot of actual comparative information at that point.
Yeah. Okay. I was it Christopher, if you're still online. I don't know if he is. Maybe not. Okay. The other just survey, we've done some work with partners, Jamie. Oh, maybe Jamie's not here either. Oh, there you are. I was interested, like observational bias. You said you did mail out survey instruments. I was wondering, does that catch like the older crowd versus say online survey instruments?
Yeah, we've done both, and I think in this case we actually had an online option, but it was sort of quasi online. So that if you wanted to, you could take a little bit.ly and enter it into, but you had to manually type it in. It was a short one. We find that whenever we do the hybrid, both, this isn't an email where you can just click a link. You actually have to physically put it in a web browser. It's like 70, probably more like 80-20, 80 mail back and 20 online. And there's certainly a generational difference.
Yeah, interesting. It's a fascinating thing to try and elicit people's ideas of things. Much easier running numbers on power transfers and
yeah.
Cool. We're coming to the end of our time pretty quick. Is there any other kind of final questions people had? No? Okay. Well, with that, maybe we'll wrap up. Thank you, everyone. Thanks for the presenters. Great cross-Canada look at this, and certainly it's coming to a country or ocean near you. So thank you for everyone, and looking forward to future conversations. I'm certainly very interested in connecting the East and West Coast. So connect up with a number of you offline. I think I got some things we could chat about going forward. So just yeah, thank you for everybody, and we'll see you next time.
Thanks,
Is there
Graham.
anything else, Marianne, you want to announce at the end here? Or?
Thanks, everybody. No, just thank you, everybody, for all the presenters, and Curran for moderating. And please join us on Wednesday for asset management.
Perfect. All right. Have a good day, everyone.
Bye.
Cheers.
Thanks, everyone.